This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
So welcome to lecture 15 of the Winter School. We now have all the important technology collected in order to talk about Einstein gravity. Now recall that in Newtonian spacetime, which we talked about in lecture 9, we were able to reformulate. So it's just a reformulation, it's not new physics. We were able to reformulate the Poisson law, that the D'Alembertian of the gravitational potential is 4 pi rho, where rho is the matter density that produces the gravitational potential. We were able to reformulate the Poisson law in terms of the Newtonian space-time curvature as R00, it was the 0,0 component of the Ricci tensor with respect to the Newtonian connection that we identified, and that was 4 pi rho. Sorry, there's a gn missing, g sub n, and here's a g sub n rho, and g sub n in general here is the Newtonian gravitational constant. That's, for instance, the one you measure in this Cavendish experiment with the 2 big balls. Okay, so we're able to reformulate the Poisson equation like this. Now this was in Newtonian space-time, and however, relations of this form prompted Einstein. This prompted Einstein. Of course, Einstein thought about this in many different ways, so it's difficult to say what exactly prompted him to do what in the course of the development of the theory, but roughly speaking, this prompted Einstein to postulate in the years before 1915. I'm not exactly sure when he wrote this down, maybe 1912 or so, that the relativistic field equations for the Lorentzian metric G of space-time as we defined it this morning, so of relativistic space-time, if you want to put emphasis on it, it prompted him to postulate that the relativistic field equations ought to be RAB equal 8 pi g Newton TAB. The 8 has to do with the conventions for the factors. So it's R00 is rho, and R00 is again connected with the energy density. We saw that if you go to the 0,0 component with respect to some observer, you get something like this. But then this split, that 0,0 is special, has to do with the absolute time. Einstein said, well, we don't want that. We don't want that direction to be special. So it ought to look like this. However, this equation suffers from a problem. And the problem is that the right-hand side, if you raise the indices and so on, but by the way, so I'm now using lots of indices, so I seem to be in a chart all the time. And yeah, you can view it like that. If you know what you're doing, it's perfectly fine to be in a chart. But you can also look at this like, this is not in a chart at all, that would be Penrose's view. A quick way of writing what you want to say. Okay, Anyway, so we take the view, you're in some chart, but it's true in all the charts, so who cares, right? This is just much quicker notation than if I wrote everything chart independent. The important point is it is chart independent, what I write down. You could check it explicitly. Okay, anyway, so if you take on the right-hand side this divergence over the first index of this tensor, we know from the matter theory that this yields 0. This has to do with the fact that the matter theory has been formulated from an action, and this action was formulated without, or could have been formulated without the choice of coordinates, and that yields you this kind of conservation law. Now that's the right-hand side. Now on the left-hand side, you have a different situation. If you take the derivative of the Einstein tensor and then you contract over these two, Einstein tensor, of the Ricci tensor, this is Ricci, right, the Rick guy. I can write it like this because here you see it's Ricci, not Riemann. This is not 0 generically. It might, in certain situations, it might be 0, but generically it isn't. Now that's not good for an equation because obviously I could take this divergence on both sides and it leads to a contradiction. And so what do you do? So Einstein tried to argue this problem away. Gravity is different, you know. You all don't understand. But nevertheless, it's wrong. Nevertheless, the equations cannot be upheld. So those are not the field equations. Now, what is the solution to this? Well, the solution came by Einstein, but at the same time by Hilbert. Hilbert, as you all know, one of the most famous mathematicians of all time, he was actually a specialist for variational principles. For variational principles. And he recognized that this is because this comes from an action, so he thought, why not derive the left-hand side also from an action? So Hilbert suggested to solve or to find the appropriate left-hand side of the field equations, of the gravitational field equations. Hilbert suggested to start from a variational principle. From an action. And so, as Hilbert, he said, why don't we write down an action for the G? It's a field theory, so it must be over the entire manifold. Well, what is the simplest function I could make of the metric? Well, I could contract it with itself. That's the dimension. That's a very boring function. Actually, from Riemannian geometry, one knows that the simplest function one can build from the metric, its first and second derivatives, is R. From the first derivatives, you can't build any tensor. And from the second derivatives, you can build the Ricci scalar, which you remember is RAB, GAB. That's the simplest function. But of course, if you integrate a function over a manifold, you need to have a density here in order to make the whole thing work. So by the rather obscure principle of simplicity, simplest action, one might arrive at something like this. Now, of course, you can talk about the beauty of equations. You can talk about the simplicity of equations. the equation being economical and the shortest and whatever equation. All of these are aesthetic arguments that have nothing to do with physics, right? If physics followed aesthetics, planets would run on circles and not on ellipses because the circle is more perfect than the ellipsis, right? So it's obvious this is not a good guiding principle. On the other hand, if you're a mathematician, you can say, oh, these physicists, they're just writing down equations just like that and they get inconsistencies. Well, let's see what I can get if I start with the simplest here. Maybe I get some insight on how this left-hand side must look like. So that's roughly the idea. Now, in the following, many people for many years have thought about how to justify the Einstein equations further, and I will probably talk about this at the end of the course, where if time permits, I will also explain that this action is the unique one you can write down if you want to have Maxwell theory on it, and that Maxwell theory ought to be predictive and quantizable. But anyway, that will be later if time permits. So we start here. This is what Hilbert just wrote down in order to write down something he could vary. Okay. So, well, that's essentially, that's a fair statement, right? I mean, anything else is interpreting something into it which isn't really in there. Now, so this is Hilbert's suggestion, and the aim is varying this with respect to the metric GAB will result in some tensor that one can show abstractly, that if you vary such a scalar function with respect to a tensor, it will result in some tensor G up AB. Okay, and if there's nothing else to it, it would be G up AB equals 0 because we didn't add a matter action. You would get something like this, and the question is, what is this tensor capital G that we get out of the variation of this with respect to the metric? Well, there's only one way to find out. So variation of S. Hilbert. We do it. Okay. Now, you know, variation leads to the Euler-Lagrange equations if you don't specify the Lagrangian. Then you get very general equations, you can work them out. Usually it's quicker to vary anew rather than writing down the Euler-Lagrange equations, but you just do the variation again. Now, variation, if you really write it down for point particles, involves deforming curves and so on. Here it involves deforming fields. But there is a quick way to determine the variation by just some symbolic calculus, and you probably saw all of this before. I just do it again in this quick way because this is really very useful. Okay? For a proper mathematical foundation, you look at any book that does that properly. But what I do is right. It's just at some point I have to say, well, variation behaves like differentiation, which it actually does. Okay, so we vary the action. It's understood that the variation is with respect to the metric. Okay? Okay. And we require that the variation vanish. And that ought to give us the field equations. Now, what is the variation of S. Hilbert? The variation of S. Hilbert is the following. M. So now we have in here the square root of minus the determinant of G. We have in there the GAB that contracts and the RAB that depends on the G, its first and second derivatives.
Why do you want the GAB to vanish? Should be divergence free, that's what we wanted in the beginning.
No, this is, if I vary this action, the variation of this will yield a tensor GAB. Now, if I added here plus S matter, I would then get on the right-hand side a TAB, and I have the field equations. It's just that I denote the variation of this action by GAB. And I already wrote the equal to 0. If you add nothing else, that's the vacuum field equations. So maybe I should say varying this with respect will result in some tensor GAB is probably the better statement. Okay, so
One more thing.
yes.
So the stress energy tensor is divergence free. Usually it's just called energy conservation, and I thought it's physically motivated. I don't quite see how it follows from deriving from an action.
It follows because in the action, if you formulate this chart chart independent, you can actually show that this implies a Noether theorem that gives you that. That's the point. So this can really be shown from there. Okay. So you vary, well, you have to vary this, this, and this. So the variation is like a derivative. Well, that's the first of these rules. So it varies the first factor plus it varies the second factor and keeps the others, plus it keeps the first and the second, and it varies the last factor. This is what variation does. Have you seen stuff like this before in classical mechanics? Probably, yes. Okay, so here it's done for fields, but it works very similarly. Okay, so obviously we have to solve three little problems. The first one is we need to find what is the variation of the square root of minus the determinant of g, what is the variation of the inverse metric rather than the metric, and what's the variation of the Ricci tensor. Well, let's do this one by one. So let's call this term 1, term 2, and term 3. We need to get them under control one after the other. Okay, so at 1. The variation of the square root of minus g, essentially it's a derivative, is first you get rid of the outer derivative, and out here you have minus, and the derivative of a determinant is the determinant itself times, okay, I should write determinant to be clear. It's the determinant itself times the inverse of the matrix of which you take the determinant, that's this one, times the variation you're actually looking at. That's this. Okay? Right. So how can you see this? So in here goes that the variation of the determinant of g is the determinant of g times gmn delta gmn. How do you see this? E.g. from, I'm not going through this, the fact that the determinant of g is the exp of the trace of the ln of g. This is one way to look at that. Okay, so you get this, and we have this here. The result is 1/2 square root of minus g gmn delta gmn. This is the first lemma we have here. Then at 2, you have the variation of the inverse metric. Well, how do you get this? Well, if you have GAB and you have GBC, you know this is delta AC. That's clear. So therefore, now varying on both sides, you have here the product rule, delta GAB times GBC plus GAB delta GBC equals 0. I applied the variation to both sides, but then I can isolate this by pulling the g to the other side, and this gives you delta GAB equals minus GAM GBN delta GMN. And I renamed indices in the last line to make the result look more memorable. Okay? So it's the second little result we're going to use here. Now before we do this, let me do the third here. There essentially we have to figure out what is the variation of the Ricci tensor. Now this is more tricky. Nevertheless, we're able to do it with our technology. Now the Ricci tensor, if I go to normal coordinates at a point, and I can consider the variation at the point. You go to normal coordinates. The Ricci tensor is the partial gamma. So it should be d by dx, whatever I write down. I write this in short form like this. M A M, comma B minus del gamma M A B M, and normally you would have plus gamma gamma minus gamma gamma with certain contractions, right? You saw this, but because we're in normal coordinates, these go out. The derivatives remain because normal coordinates are just at the point, So the next point it could be different, but these guys go. But now we take the variation of this. So it's the delta of this and the delta of that. Now the next step consists in observing, and in fact I can formulate this here as a nice rule, that these guys commute. But how do you know this is right? Well, you have to formulate the variation more properly. If you do, you see it does commute.
Sorry?
Yes?
Why are you allowed to evaluate all varying?
Pardon me?
In the first line, the last thing,
Yeah.
You evaluate first at the normal coordinates before you varying.
Before I vary?
So
Yes, because variation means you choose two different gammas. Yes.
and both are zero in this coordinates.
Yes. And so then you get here minus del m delta gamma m ab. Well, even if you didn't, look, stop, Julian. Even if you didn't do this before varying, you would here have a delta gamma gamma. That would be a delta gamma times gamma plus a gamma delta gamma. Here a minus delta gamma gamma minus gamma delta gamma. You agree? Still, at the end, there's still one gamma in there that nils this. Okay, so you go to this line here, and now there's an important observation. The delta is the difference between two gammas, because I take a gamma and I compare it to another gamma. Now it's a fact of life that if you have one gamma, gamma ijk, and I subtract it from a totally different gamma, a different choice of gammas, a different connection coefficients, ijk, both with respect to the same chart, that these are the components of a 1, 2 tensor. Why is that? Well, because under coordinate transformations, this guy picks up an ugly term. It transforms as a tensor up to an ugly term. But the ugly term doesn't depend on the gamma at all. It depends only on the change of coordinate system. Remember? dy by dx, d2x by dyy. This one also changes in its linear term, like this takes a tensor term, this contributes, and the extra term is exactly the same, but you subtract. So the extra terms cancel. Hence the difference between two connection coefficients, two different choices of connection, is a tensor. Two connections differ by a tensor. Now this is important here, because we're still in normal coordinates. We've chosen them once and for all for this calculation. So if the difference here is a tensor, and this is a tensor, then in normal coordinates I have this del b, and you say, oh my god, I can't derive tensor components like this. Well, the point is you can take this tensor and you can even make of the partial derivative or covariant derivative without harm, because the difference between the covariant and partial derivative is gamma terms, right? But the gamma terms all vanish because we do normal coordinates. So I can write it like this. I mean, this is rather remarkable. I mean, there's a gamma which usually you can't take a covariant derivative of because this is not a tensor, but we see it is a tensor, so we can do all this game in normal coordinates. Minus nabla m delta gamma components m, a, b. Aha. So now we did this, and at that point we can't make any further progress until we realize, but there is not this term interesting. Interesting is this entire term. So let's try to figure that one out. So hence it follows the square root of minus g, gab delta rab equals. Aha. So square root of minus g. Now this gab is actually in front of this, right? But I can, without harm, pull it into this. And I should introduce some notation that is very useful. Notation. If you have a tensor, say a 1, 1 tensor, and you take its derivative in the b direction, and you have an I and a j, then this, from now on, or sometimes, I will write a, I, j, semicolon b. The semicolon says take the covariant derivative in direction B. But don't think you take the covariant derivative of the components. This symbol means take the covariant derivative of the tensor, and then that's the component from the tensor out here. Okay? Very important. So I could write this guy here as delta gamma MAM semicolon B, and here delta gamma MAB semicolon M. Okay? So now I use this here. I go maybe a line below, equals square root minus g. Now I can certainly pull this g into the semicolon. Why? Well, because it's the metric compatible connection. So GAB delta gamma MAM semicolon around it B. Why? Well, it will satisfy a product rule. It will take the covariant derivative of the g times this guy plus g times the covariant derivative of that guy. But the covariant derivative of g or g inverse is 0 because of nabla g equals 0. Okay? So you can pull this in without harm. That's this first term minus square root of minus g. GAB gamma, delta gamma, importantly, MAB in brackets semicolon M. Ah, that looks much better. Why does it look better? Because if you look at this, here this index M is summed over, this index A is summed over, all that's left here is an index B in here, which is then being derived, but because this is a tensor and this is being summed over, in here are vector components. So I say, I can identify that there's a vector A with components B, and the vector is covariantly derived with respect to B, minus square root of minus G. This is a different vector because here, gamma MAB, there's the A summed and the B summed. That's a different vector from this one. It's called the vector B. Up M semicolon M. Aha, why is this interesting? Well, this is the divergence of a vector, this is the divergence of another vector, but remarkably, because this is summed over, you can check that this is the same as if I did square root of minus g. I took the AB and I take the partial derivative in direction B, yields the same result, because the corrections that come from here are actually corrections that come here by application of the product rule. Minus square root of minus g, b, semicolon b, or mm, doesn't matter. Okay? Yes?
Please explain again why the difference between these gammas is a 1-2 tensor.
Aha. So a gamma in the Y system, ijk, is the gamma in an X chart, MNQ, with d by d, d by d, d by d, xm, x, y, hang on, no, there must be a yi here. No? I thought there must be yi, xm, xn, xq, yj, yk. Isn't that right? Yes. Plus d2xm by dyj, dyk, dy by dxm up I. Isn't that the right term? Okay, so this is for this connection gamma. Now I write this down for an entirely different connection in the same frame. What I get is exactly the same terms here, but here there's a gamma twiddle, MNQ in the X frame. But this term is precisely the same because there's no gamma appearing. Now the difference between the two will transform without the extra term because they cancel. Okay, Good.
I have one more question.
Yes.
The A, B, B, and B and M, are they both tensors? No, they are.
A and B are tensors, as you can read off from here. They are the tensors defined here. This is the AB, and this is the BM. Well, look at it. It has tensor component. It's a delta gamma. What do you mean? No? It is. So you have a delta gamma as a tensor. It has components M, A, B, but you have a contraction here that makes it a covector field or covector. Then you pull the index up. It's a product of tensors. It's a contracted tensor product. It's a tensor.
So my question was the difference between the last two expressions. So the last equals that. You just put some brackets.
How you get from here to here?
What's the difference?
Yes. Oh, the comma. I am sorry. The comma is the partial derivative. So pardon me? Semicolon is. I'm sorry. Only comma. Comma is partial. Okay? And then you have a product, and the partial goes on this guy, and this guy will reproduce itself, but also produce the gamma symbol that goes with the A, not the full gamma symbol, but the right contracted gamma symbol. Okay? Yes?
I do not see this first part where, yes, it's determined by exponent trace logarithm of metric tensor. I don't see how.
Yeah, okay. So, well, if you vary exp, you get exp. Trace lng, that reproduces the determinant again. But then you have to take the inner derivative, and the inner derivative of ln is 1 over. That's the inverse. Okay, so now if you want to have it more precisely written down, the cleanest proof is via the expansion formula for the determinant, where you expand in a line with the minors or the adjuncts or whatever that's called, where you cross the i's in the jth line and take the determinant, tralala, and there you can, in a one-page calculation or so, you arrive at this formula. Okay, so this is the quick way. I don't want to go into the detail here, right? So this can be shown. Okay, so we have collected the terms 1, 2, and 3, and it's time to write this up. Collecting terms, one obtains 0 is delta S Hilbert equals M. Now, the variation of the square root of minus g was 1/2 minus square root of g, g mn, delta g mn, right? That was the first term, which came with another gab, rab. That's the first term. Plus, now, there comes another square root of minus g. Now variation of the inverse metric yields a minus gam gbn delta gmn, and it came with an rab. That's the next term. The third term comes with a plus square root of minus g gab. But now this variation over there, which I need to quickly peek at before it's wiped out. Ah, yeah. Okay, thank you. Times. Aha, I already used this up, right? In this over there, I don't need to write this anymore because I already included all of this. This becomes square root of minus g some vector a, I'm not even interested how it looks in detail, comma a, minus g some vector b, I'm not even interested how it looks in detail, comma b, close bracket. Okay, that's this. So now you have an integral over a volume, and what kind of term is this? if you have the derivative here and it's contracted like this? Is a divergence, right? And yes, exactly, or Stokes or whatever. So it is a surface term. And this is also a surface term. So if you're not very careful, you say you can discard them. They're zero if there's no boundary. Well, you see, in point particle mechanics, you fix two endpoints, and then you do this variation, and you take care that at the endpoints things are fixed. If you want to do this field theory calculation properly, you have to fix an initial surface and a final surface, and you need to fix the fields there and vary them in between. And then if you want to do this properly, you also fix them on the boundaries here, right? And then maybe you take the boundary to infinity and so on. That's somewhat subtle, okay? So in the action, there may be surface terms that survive if you want to have the action, as the value of the action. However, for the equations of motions, they really don't make a difference, so we can take them out for the equations of motion. Okay? That's it. Okay, so we do that, but what are we left with? M. We can factor out the the square root of minus g. We can factor out the variation, the arbitrary variation delta gmn, and what we end up with is 1/2 g m up mn r, because this is r, minus, this has the indices pulled up, rmn, equal to 0 for an arbitrary variation. Because that variation is arbitrary, we can conclude from the vanishing of the integral for an arbitrary variation, the square bracket must vanish. Hence, we obtain that our tensor gmn equals, well, I should have said that this tensor that comes out is called minus gmn. Okay? I mean, I didn't make a sign mistake, so it's just a question of how I call this guy. Gmn equals, I should have written minus gmn before when I said Hilbert wants to derive this, and then you get rmn minus 1/2 gmn r. That is what Hilbert gets out. So hence, Hilbert, from this mathematical argument, one might call it, from this mathematical argument, concluded that one may take RAB minus 1/2 GAB, R, which is just the same objects with the indices pulled down with the metric, equals 8 pi GN T AB. And in fact, Einstein, by physical arguments, arrived at the same result, more or less at the same time. So these are called the Einstein equations. Hilbert is not mentioned, but the action that I called Hilbert are today called the Einstein-Hilbert action. And I think everybody agrees that does both of them justice, because Einstein came here by physical arguments again, and well, Hilbert just, in a sense, scooped Einstein by listening to one of his talks, hearing about his problem, saying, let's try this, and doing this little calculation. Okay? So these are the equations on which general relativity today is based. Now still, there is, at this point, no better argument for this than saying this is a pretty nice compact action, right? So one can, of course, argue whether that's a good reason for a physicist or not. Okay, So then we have a third solution of the nabla A TAB equals 0 issue. One can show, in fact you will show in the tutorials, that this so-called Einstein curvature, that the Einstein curvature, which is this 0-2 tensor GAB equals RAB minus 1/2 GABR, so exactly the left-hand side of the Einstein equations, that this Einstein curvature satisfies the so-called, that's just the name, but you find in the books under this name, contracted Bianchi identity differential, contracted differential Bianchi identity. You wouldn't have guessed it. This equals 0. Okay? So the issue is indeed solved, and it had to be solved because this was derived from an action where the same argument that leads to the nabla A to the divergence of the energy momentum tensor being 0, that was your question, the same argument leads to that this must hold. So if this didn't hold, then somebody somewhere made a mistake. Okay. Yes, so this solves this argument, and it shows, well, Einstein really forgot this term, and this is a term that comes up by this consistency argument. Okay? Yes?
Are there any intuitive physical explanations why Einstein arrived at this as well?
Well, there are a number, and over the years, people... so, for instance, you can look at fluids, and so you can fill space-time with a fluid, and one understands kind of, or already at the time one understood relativistic fluids, how do they behave, and you can then make consistency arguments, and you pick up this term. Okay. There are many other ways by which you can arrive here. A way that's a recent result how you arrive there is you require that you have dynamics for your space-time that is compatible with putting Maxwell theory on it, such that the Maxwell theory remains predictive and is quantizable. And that already fixes the Einstein equations. As I said at the end of the talk, the school, I will talk about this. Yes?
The Newtonian spacetime are this I is 0.
In the Newtonian spacetime, which is 0? No, you can't even construct it, because in the Newtonian spacetime, the Newtonian spacetime only carries a connection, but this connection does not derive from a metric on Newtonian spacetime. It's a connection that doesn't come from a metric. And if you don't have a metric, you cannot construct the curvature scalar. Because from a connection, you get the Riemann tensor, 1, 3, and from that you get, by contraction of 1 and 3, you get the Ricci tensor that you get from a connection. But you don't get these two indices away unless you have a metric in the game as well. But there is no metric connection. So Newtonian spacetime, we only talked about autoparallels. And if you remember, I presented you a Newtonian picture before we introduced metrics, because I didn't want you to get confused. So the Newtonian spacetime, don't laugh. So the Newtonian spacetime carries only a connection, but not a metric. So you couldn't even build this guy. And in Newtonian spacetime, we only found that the 0, 0 component of this guy is this 4 pi g rho. Right? But I could not even say, and all the others are 0, but I could not even say what the scalar was. Okay, so this heavily relies on the fact that all the connection that these curvature tensors are built from the Levi-Civita connection of the G. These are the metric curvatures. Further question? Yes?
So through those surface terms, do they have anything to do with the cosmological constant?
No, they do not. I'll discuss the cosmological constant in a second. They do not. They do not. Yeah, no, they do not. They do not. Yes?
Could this somehow be interpreted like current on that surfaces?
These guys? A current on the surfaces. I don't know. But the issue is that if you go to these surfaces, like here, you can fix the points and you can fix, but you cannot fix the velocities at the same time. Now, this guy here, the Hilbert action, depends on the metric up to the second derivative. And some issues here are you can't fix the second derivatives as well. You can fix the metric and the first and so on. And so you have to discuss this very carefully, what happens at the boundaries. That's the point. Okay? And this was only discovered later that you have to do this. So I think Gibbons and others, they looked at this, at these boundary terms, and they play a role in the canonical formulation that Domenico Giulini is going to discuss, one of the satellite lecturers. There one usually takes good care of these guys, one needs them, but for the equations of motion, they really drop out. Okay, so they only play a role in the absolute value of the action, not for the equations of motion. Okay? So then we finally look at variance of the field equations. And I don't mean variance like other gravitational theories. I mean the same field equations, a little extended or a little differently written down. So the first one is a simple rewriting. Simple rewriting is the following. So let's again write down the field equation. I mean, this you need to know by heart. This is the key point of this course. 8 pi g n t a b. Now, maybe for the future, just for the heck of it, we will set this to 1 over 8 pi so that I can finally get rid of these annoying factors, right? And in fact, I think there's also an over c squared in there, which I already set to 1, so who cares? Okay. So let's assume these are the field equations, right? So, So now I can, on both sides, contract with GAB. I do a full contraction. What do I get? What is RAB fully contracted with GAB? R. What is GAB contracted with GAB? 4. Thank you, dimension of space-time, 4/2 is 2. R minus 2R equals T, where T is defined as TAB, GAB. Okay? So now, therefore, I have R minus 2 as minus R. R is minus T. Agree? So I go with this into the original field equations. I have RAB minus 1/2 GAB T with a plus equals TAB. Or RAB equals TAB minus 1/2 its trace GAB. So I can call this right-hand side the modified energy momentum tensor T hat AB, where from the energy momentum tensor I subtract 1/2 times its trace, so contraction with G, times GAB. And what do I then have? Then the Einstein field equations, after all, take the form RAB equals T hat AB. So Einstein wasn't that wrong after all. He just took the wrong version of the energy momentum tensor. This is an energy momentum tensor with a modified trace. Okay? But of course, T hat no longer T hat AB equals 0. Right? It's just a simple rewriting. So if you wish, you can relate the Ricci curvature directly to an energy momentum tensor, well, a modified energy momentum tensor. Okay? So sometimes it's useful to write it like this. It's just a simple conclusion from the field equations themselves. Okay? And the second variant is indeed different physics. And the second variant is if you do the Einstein-Hilbert action, m square root minus g r, and in here you write plus 2 capital lambda. And now this capital lambda has a name. It's called the cosmological constant. And it's nothing mysterious. It's just a constant that you add. Well, let's interpret this in a second, but before that, let's look at the history of this cosmological constant. So 1915, right, I think, Einstein said it must be there. Einstein said the cosmological constant is there and it's less than 0. Einstein wanted that. Why? Because only if you put that there do you get solutions for cosmology, for the history of all of space-time, that produces a static universe in order to get a non-expanding universe. Because to Einstein at the time, it seemed ridiculous that the universe should be expanding instead of just be sitting there. So he wanted this constant. Then later, of course, Hubble saw the universe is expanding, which is perfectly compatible with lambda equals 0. So Einstein said this was my greatest blunder, I shouldn't have done that, this is so unaesthetical and and he said lambda equals 0. I mean, no doubt there are many papers on why lambda must be 0. Okay. So now today, lambda is supposed to be bigger than 0. Now it's supposed to be bigger than 0 in order to account for, and we'll see this in detail, I'm just giving you the taste of it, to account for an accelerated expansion. So the universe doesn't only expand, it expands in an accelerated way, an accelerated expansion. Today the problem is that this lambda is supposed to be bigger than 0, but very, very small. Okay, what do you mean by very small? Well, very small compared to any effect we could imagine that produces a non-vanishing lambda. Let me clarify this. So if we now do here the variation, the lambda contribution here can of course be understood as a contribution to matter, right? Because if you say this is still gravity, then this part could already belong to a matter action, right? So lambda non-zero can be interpreted as a contribution, what is it? I think minus 1/2 lambda GAB to the energy momentum of matter in space-time. And you say, yeah, okay, why not? Well, look at what that means. That means constantly, over all the universe, there is a lambda, there is energy everywhere provided by the lambda. It's not just where the fields are big or where the fields are non-vanishing. It's everywhere. Everywhere where there is a metric, and the metric is everywhere, there is this energy. And so people call this dark energy. It doesn't interact with anything, but it contributes to the curvature of space-time. That means it's dark. Yes?
No, the terms that we threw out, the divergences are constants, which give us lambda.
And
one can, as I said, one can carefully treat this. For instance, so for a careful treatment of the surface terms, which we discarded, see, for instance, Eric Poisson, A Relativist's Toolkit. Excellent book. It's, I think, Cambridge University Press. But the point is, this is at the level of the equations of motion where you identify this, so it couldn't come from the surface terms. The surface terms are the action level. This is the level of the equations of motion. Now, this lambda, what could give rise to an energy that's everywhere and we haven't thought of before? Well, yes?
What is a constant over a manifold? I can imagine a constant over real numbers, but a constant over a manifold.
Well,
There's no structure in our space-time.
well, if you calculate the volume of the sphere, you integrate over the function constant 1. Right? It's the volume of the sphere. Now you take capital lambda times the volume. You can pull it out of the integral. Times 1. So it's lambda times the volume of space-time in the action. And then you have to vary. Okay? So the point is, you can write this there. It doesn't destroy the Bianchi identity. And the question is, what could this physically be? We haven't thought of it so far. It seems to be there. And then people like Weinberg got the idea it could be the vacuum fluctuations of quantum fields. So we have a number of quantum fields in space-time. Now they have vacuum fluctuations, right? Electrons and positrons come into existence and annihilate each other again, right? It could be this vacuum energy. And then Weinberg calculated the vacuum energy, I think, from QCD and how it would contribute to this lambda and whether it would suffice. And so you can get the following calculation. So idea, lambda could come or could arise as the vacuum energy of the standard model fields. So this is throwing in a little bit of quantum electrodynamics, but it's quite reasonable to try that. And then you obtain lambda calculated this way is a whopping 10 to the 100 times bigger than the lambda observed. And this is called the worst observation of physics. The first not the worst observation, it's the worst prediction of physics, right? So indeed, we have an idea what the mechanism could be, but it overestimates by a factor 10 to the 120. So that shows that if people say it's not understood why we have a positive, so small positive cosmological constant, right? It's a puzzle where that comes from, but if you put it there phenomenologically, it fits the observations about the universe. We'll come to that later. Okay, so let me wrap it up here. In the tutorials of this week, there won't be a central lecture till Saturday, so that you can fully focus on the satellite lecturers. We got great people, so you should definitely come. But in the tutorials, they will run on for the central lecture. You will check that the so-called Schwarzschild metric, you must have heard that, the so-called Schwarzschild metric is the spherically symmetric solution of Einstein's equations in vacuum. And Einstein actually wrote, when he set up the equations, he said, well, these equations are so complicated, nobody will ever find an exact solution. Okay, approximately yes, linearized solutions yes, but exactly no. And then Schwarzschild in 1916, the legend has it that he was even injured and was on a hospital bed, so maybe my voice helps me today with other research. He actually said, well, let's make a symmetry ansatz, and he derived the exact Schwarzschild solution. Well, under these spherically symmetric assumptions, you will check that the Schwarzschild metric and the metric that's called as the Friedmann-Robertson-Walker metric that describes a homogeneous and isotropic universe, and that PP wave metric, which describe PP waves, as you can imagine, and that the Reissner-Nordström metric, which describes the spherically symmetric solution of Einstein's equations around a charged body, that all of these, you will check that all of these are solutions to Einstein's equations. That means you will be asked, well, in groups, there will be the advanced tutorials. So these will be what we called workshops or advanced tutorials of physics applications, whatnot, has different names. There you will check, one group will check this, the other this, the other this, the other that. Okay, and you will work in teams of 3. And you must, it doesn't matter which one you check, we'll tell you anyway, but you need to have done this once. You get a specific metric and you plug them into the equations. It gives you the same insight like in high school when you see something like, what is it? Is it like this? It's like that? It's like this? Who knows? Okay. Plus. It must be a plus. Okay. If you see for the first time that this is solved by x of t equals cos omega t, right? Or sine omega. See, what this, by a function like that, that's funny. Well, you know it works like that, okay? So it's the same thing, and you must plug it in once, and then you know how this works. Then you really have a feeling for what it means to be a solution. Okay, that's one thing you're going to do. Another thing you're going to do is you're going to discuss, so that's in the advanced tutorials. In the elementary tutorials, that's the tutorials you had so far for the mathematical foundations, there you will, in the familiar manner, you will study motion of particles and observers in Schwarzschild space-time. Okay, that's a very interesting topic, and it will lead to results that will be needed in lensing. And then there will be satellite lectures during the week, during this week. Next week there are 2 others. The first ones will be by Markus C. Werner, who will also give a history club, which will be very interesting. And Markus will talk about gravitational lensing. Gravitational lensing. And I think he will show things like, you see, if you have a body here, there's a star here, and you look here, you know, light goes out in all directions and it's bent here, which is, by the way, something you will study on Thursday in the advanced tutorial as well. That's the first advanced tutorial. Second advanced tutorial, you study here the bending of light. Then you know you see a star here, or you think you see one, and you see one here. You see 2 pictures. And Markus will show under which circumstances you see always an odd number of pictures, and he will show that with Morse theory. It's quite interesting. And we have Domenico Giulini. And I asked him to show something very important, namely, actually, what are the Einstein equations, the dynamical equations? It seems like, boom, space-time is there. You solve the equations, and you have all of space-time. But where's the evolution? And he will show that, very roughly speaking, if you think of the 3 metric in some space, that the Einstein equations tell you how the 3-dimensional metric, you can pull back to a spatial surface, how that evolves in space-time. And what this requires is to reformulate the Einstein equations in Hamiltonian form. And so that's called canonical formulation of gravity. And that yields you a lot of insights. So that's also very important, and you should really look at that. And that also has been followed for many, many years in order to make progress in quantum gravity. So it's the key to quantum gravity if you want to go there. So I invite you to all these, to the elementary tutorials, of course, to practice the stuff we did here, to the advanced tutorials, to get a feeling for the physics. You're going to do this, and you're going to study this, and also the precession of the orbit of Mercury, how it goes around the sun rather like this, and you calculate this. This here goes at 4 arc seconds per century. No, 42 or something. Arc seconds, or what is it? 40, pardon me? 42. 42 arc seconds per century, this precession. This was long known before Einstein. Einstein was the first one to explain this, and you will derive this result from data using Einstein's theory. So I invite you to all these parts of the school this week. Thank you very much.